You'll be pleased to learn that the next topic is quite a bit easier. We're going back to the tiny machine, but instead of engaging with programs that have already been loaded as a lump of hexadecimal into the tiny machine's memory, we're going to work with these more human-readable programs that we can translate into hexadecimal. And the first thing I need to teach you to do, and it's usually worth 3 marks, is to just make that translation. So this is a program in tiny assembly language where instead of getting a lump of hexadecimal, you get a sequence of instructions. Each instruction has an operator, and sometimes, as you would expect, those instructions also have operands. But quite often, the operands are given as words or as formulae in terms of words. These words we call labels. And then to the left-hand side, where you see on the left a label with a colon, that's what's called a label declaration. That's telling you where it is that the label is talking about. So in order to understand what start means, what loop means, what load means, we have to see where it is declared in the program. And once we know that, we can figure out how to translate the program into a lump of hexadecimal. So let me first of all explain how you do it. You do it in 2 phases. First phase is figuring out what the labels mean, and the second phase is translating all of the instructions. So how do you do the first phase, figuring out what the labels mean? You do it by making a running total of the instruction sizes. So let's do that. You start at 0. So that tells you that the start label means 0. Okay? Now, LDA has an operand. We can see its operand is this thing, this word 0. So that's to say, it's going to take up 2 memory locations. So we add 2 to our running total. Everyone see why I added 2? Because the first instruction had size 2. And we're making a running total of the sizes. So that means that this loop label really refers to location 2. Okay? So what do I put here? What's the next? Yeah, it's another 2-cell instruction. So our running total goes to 4. What's next? 6, because that's another instruction with an operand. What's next? 7. What's next? 9. What's next? A, then C, then E, then F, and here we've got just storing a data value 0, so that takes up 1 cell, and then if we add the size of that data, we get back to 0. So that tells us that if we put all of that stuff into the tiny machine's memory, the memory will be filled up exactly. So it's important to do the last step, and if you get 0 exactly or less, or you don't even get up to going round to 0, then you're fine. If you bust the size of the tiny machine's memory, which I do all the time when I'm making up tiny questions, then it's not going to fit into memory, and there's a problem. Okay. But the crucial thing is that we now know the values of the labels. We know that start is 0. We know that loop is 2. We know that load is 4. We know that the label 0 refers to location F. I've labeled this location 0 because it has a 0 stored in it. But the meaning of the label 0 is F, because that's where in memory that 0 is going to get stored. So we're just figuring out where in memory these bits and pieces are going to get put. Okay, so I think I've got just enough space here if I write out a bunch of decimal digits. To do phase 2, so you've got to translate 3 different sorts of thing. You've got to translate operators, you've got to translate operands, and you've got to translate data. Okay? You translate operators by looking them up in the tiny guide. So here the first operator is LDA. We look it up. LDA is 4. That means in memory location 0 we're going to put 4. Does that make sense? Yeah? And then the operand is the label 0. So now that we know the meanings of the labels, we should be able to translate that operand. What do we put in the next memory location? F. We figured out that the label 0 refers to the address F. Not what's stored there, where it is. Okay? So what's our next operator? STA, which is 5. And our next operand is a formula that refers to load. What does load mean? 4. So what do you think load plus 1 means? 5. Okay? Our next operator is also LDA. So that's another 4. And our next operand is also load plus 1. So that's also 5. And you can see that when we actually put the instructions into memory, they are going at exactly the places our running total told us they should. So that's a good double check. We're actually filling in memory, and they're actually going where they're supposed to be going. It's easy to make an arithmetic mistake and screw this up. So it's a good double check to see that when you actually start filling in the memory, things go where you thought they were going. Okay? Our next operator is put, and put is 7. Next, we have another LDA load plus 1, so that's another 4 or 5. Everyone happy with that so far? Next, we have an SCF. So we look that up and we see it is C. Next, we have an ADC0. So we look up the operator and it's A. How do we translate 0? That's F. That's where the label 0 is declared. Next up is jump if not 0. So that's 3. Next up is loop. What's loop? 2. Next up is halt. How do you translate halt? Look up. It's 0. So we've translated all of the instructions, but we've still got this lump of data, and it's the easiest thing. You just copy it into memory. So here, we want a 0 at location F. We've got a 0 at location F, and we have successfully assembled the program. our running total told us the program would fit into memory exactly, and then when we tried to fit it into memory, it fitted in exactly. So we know we've done it right. Okay? So has everyone got the process? Don't worry, you get to do plenty of these. There's loads of online exercises like this, and we'll do some in tutorials. We've got the easy part of the question done, which is to figure out how to turn the assembly language program into a lump of hexadecimal. So remember the two stages? They are to make a running total of the instruction sizes, so we learn what all the labels mean. Then we translate the operators by looking them up. Once we know where all the labels refer to, we can translate the operands, and the data just get copied as they are. And that is how we fill the memory with hexadecimal that corresponds to the program. Okay? So this is the process I go through every time I'm setting a tiny question, except of course I've got a program that does it for me. So I can send in a lump of text like this and have it translated into a lump of hexadecimal to go in the tiny machine's memory. So I'm just trying to teach you to be that program. That program is called an assembler. An assembler is a program that translates a program into another program. It translates a program from assembly language into machine code. So machine code refers to the actual bit patterns, and assembly language refers to a sequence of instructions where we have operators written as these sort of coded mnemonics, they're called, and operands written as formulae in terms of labels. Okay? So you will get an easy 3 marks out of me if you can learn to be an assembler for tiny assembly language. Okay? So, it's a return to the good old days of, like Huffman coding. Learn a tedious mechanical procedure, switch your brain off, just do it, and collect some marks. Isn't that a relief? Unfortunately, to get the other 2 marks in a tiny assembly question, you have to figure out what the program does. And that is where a small amount of thought will be required. And we know thought is the enemy. Okay, so let's try to figure out what this program does. Right, so part C says the program's main loop modifies the contents of memory address load +1. So actually it mentions a main loop. Hang on, what's that about? Well, a crucial thing to do when you're trying to figure out what a tiny program does is to figure out the way in which the program will flow. So what you need to do is look for the jump instructions. So here's a jump if not 0, and it jumps to the label loop. So that means that sometimes the program will flow from here back round to here whenever the 0 flag is clear. Okay. The other thing that we need to think about, given that this is a conditional jump depending on the 0 flag, is to ask what will actually cause the 0 flag to be either set or clear for this conditional jump instruction. So before that jump instruction, what can we see that might affect the 0 flag? Well, that's a long way before. What will be the most recent, when we get to this jump instruction, what will be the most recent thing that affects the 0 flag? The add with carry. So it's going to be this operation which determines whether the loop continues or not. So we're going to need to focus on what happens there. So let's just look at what we've seen. We, as ever, start at the beginning. There's some setup code before the loop. And then the main body of the program is this loop. And then when eventually the conditional jump doesn't happen because the zero flag is set, we'll fall through to the halt instruction. So you can see the way the program is going to go is that it does some setup, and then it goes around the loop some number of times, and then it stops. Is that clear? That that's what's going to happen. It's one of these strange things. Lots of people will tell you to find out what programs do by running them and testing them. I put it to you that that is already too late. You find out what programs do by reading them and understanding them. And if you don't understand them, delete them and write a program you do understand. Tony Hoare used to say, there's two ways to get a program through quality control. One is to make it so complicated that it has no obvious mistakes. And the other is to make it so simple that it obviously has no mistakes. Only one of these strategies is a good strategy. Okay, so we need to focus in on this add with carry and what would make it set the zero flag. And that's actually the point of part C of the question. It's meant to be a big hint. Right. So, suppose memory location load +1 contains the value n at the start of these three instructions. What happens? Well, the first instruction is load the accumulator. Yeah? So that means the accumulator gets the contents of its operand. Its operand is load +1. The contents of load +1 is n. So that's going to make AC equal to n. All right? What does the next instruction do? It sets the carry flag. And what does the last instruction do?
Adds the carry flag accumulator and the relocation at the label 0.
Yes, the label 0 currently stores the value 0. And we can see there is a little bit of self-modifying going on, but we don't appear to be storing anything ever to the location labeled 0. So we can be fairly confident that the contents of location 0 will remain 0. Yeah? So, what will end up in the accumulator as a result of that? N plus 1. So what's really going on is that each time round the loop, we're adding 1 to that. You can see what happens. We've basically taken the value that was stored in load +1, we've added 1 to it. If that takes us to 0, that's to say if we've gone all the way up to F and then to 0, we stop. Otherwise we go around the loop, and the first thing that happens is we store that value back in load +1. So that's telling us that load plus 1 is being used as a counter. By the way, it's a very common trick. If you want to add 1 to a number, instead of storing a 1 somewhere in memory so that you can ADC from that location, you usually have a 0 stored in memory because at the very least you've got a halt instruction. So instead you set the carry flag and then you add a convenient 0 that is stored somewhere in memory. That's an easy way to add 1 without spending a location in memory storing a 1. So that's the trick that's happening here. Okay, so we've figured out something of what's going on. Let's see, how does this program start? We load the contents of location 0. What are the contents of location 0? 0. So they go into the accumulator, and that's the first thing stored in load plus 1. So now we know that there's a 0 stored in location load plus 1. So there's a 0 here. What happens when we do LDA with that 0 as its operand? It loads 4, the contents of location 0. And then it outputs it, so we get an output of 4. Alright, need to zoom out a little. And then what happens? The rest of the loop adds 1 to that 0. That puts 1 into the accumulator. We do jump because 1's not 0. We go back round the loop. Now we're storing that 1 in as the operand of this LDA instruction. So what do we load next time we execute this? F. And then that gets output. And then we carry on adding 1 to this 1, that makes 2. 2's not 0, we go round the loop. This becomes 2. So what do we get? What's the next output? 5. And we have to be a bit careful. So we're going to keep going round the loop, outputting the thing that's in memory at the position of the counter. So we'll get 4F, 5, 5, 4. And then we have to think, when the counter is 5, this will say LDA 5. What's stored in location 5? Well, no, not anymore. We've been adding 1 to it. At the time, load plus 1 stores 5, this is location 5. What gets loaded? The 5. So there, the operand of the LDA instruction tells us to load the very operand itself. So we will get a 5 coming out, and then the 7, the 4, the 5, the C, the A, the F, the 3, the 2, the 0, and the 0. And then finally, the counter will go up from F to 0. When it's got all the way up to F, the next add 1 will set the 0 flag, so the program will halt. That's to say, this program, its behavior is to print exactly, is to output exactly the program itself. Yeah?
I'm finding it hard to see why instruction 7, at memory location 7, you've got LDA load plus 1, so you're taking that into the accumulator, putting it in the output, and then bringing it the same instruction back into the accumulator again. The instructions.
Right. So, right. So why do I do this?
Yeah.
Right. Yeah. So it's true that. So you've got to be. So bear in mind that. So this is the crafty thing. This operand here is constantly being overwritten with the counter. So by the time this is actually being executed, it does not contain load plus 1. Whereas this one stays load plus 1. So this is where we are updating the counter. Here, we're using the counter as the address to load from. And that's how come we get to output each memory location in turn. So the clue, of course, is that the author of the program is Professor Quine. And there really was a Professor Quine. And you can look him up in Gödel Escher Bach and discover what this is. A program which outputs itself is called a quine in his honor for a particular reason. And yes, it is possible, it would seem, to write a quine in Tiny. I better stop there.